What we're going to do today is I've got a virtual experiment I'm going to show you. We already know that you're expected to know those words for freezing and melting. Yesterday we talked about one that you hadn't really heard of yet. Does anybody remember that one? Start with a V. Addison? Vaporization. That means to turn something to a vapor. What is a vapor? Is a gas. Yes. So to vaporize something means to turn it to a gas. There are two ways. One is a very slow way you learned about last year in the water cycle. Which one? Yes. Yeah, if you look at the word evaporation, think about evaporation, because you're turning something to a vapor. It's a slow process. The other one is a faster version. It happens at a specific temperature based on what the material is. What one was that, Eli? Boiling. So what I want to talk about today is that, a lot of people don't think about, when we talk about the three states, that each material has its own set temperature that it will start to boil or it'll start to freeze or melt. Yesterday we looked at that beaker with the ice in it, and what temperature did the ice start to change over to the liquid form of water? What temperature, Ethan? 0 degrees Celsius, yes. Now, however, if you started out with the liquid form of water, what temperature would it change over to the solid form? Jacob?
Under 0 degrees.
Well, no, not under 0. No. That one started out at negative 15, but what temperature does water freeze? At what temperature does it turn to a solid? Laura? That's Fahrenheit. What is that in Celsius? 0. Here's the thing that a lot of kids get confused about. I said, it started melting at 0. Okay, so the melting point for water is 0. But that's also the freezing point, because if it's a liquid and you're trying to freeze it, that's the same temperature it's going to turn to a solid. So that 0 degree on Celsius, or 32 in Fahrenheit, that's the changeover spot for water. If it's a liquid, it'll start to freeze. But if it's already frozen, it's in ice form, it'll start to melt. Okay, so lots of kids get confused by that. They say, oh, wait, how can the freezing point and the melting point be the same temperature? Think of it as sort of the changeover. It'll change its phase. It'll go from solid to liquid or liquid to solid. That 0 degree spot on the thermometer is where the change will happen. So if it's a liquid, it'll start to freeze. If it's frozen, it'll start to melt. Nod your head if so far so good. Now, what we're going to do now is we're going to look at 3 different materials. And we're going to look at their freezing points or melting points, depending on which way you're going, if you're trying to turn it to solid or liquid. And we're also going to look at their boiling points. And what I want you to notice today is the temperature that each of them change over to those different phases. Okay? Now, we have already talked about all 3 of these substances. The first one, water, we're very familiar with. The other one we're going to use is alcohol. And then there's the third one is Miss Ewing's favorite element. Does anybody remember what my favorite element is? Very cool. Mercury. So we're going to use all 3 of those. And thankfully, this is virtual because we don't want to try to boil mercury around ourselves, right? Yeah, that'd be bad. Now, we're going to need a data chart for this. And the way this is going to work, we've got water and we've got mercury, and methanol is the alcohol. And there are different kinds of alcohols. We'll talk a little bit more about that later. And then we're going to heat them up until they boil. Stay with me. And then we're also going to cool them down until they turn to a solid. So here's the chart. You've got 3 columns, one for our substances, one that says boiling point, one that says freezing point. And then you've got 4 rows. The top row has the labels. And then a row for water, mercury, and methanol, which is a kind of alcohol. We're going to start with water because we're most familiar with it. And what we're going to do, you see the situation, we've got a beaker full of water. It's got a temperature sensor in it. You should be looking this way so you know what to look for. And as we apply heat or remove heat, we're going to see the temperature change. And what I need you to do is look to see what temperature it's at when it changes state. So I'm going to heat it up. Now, water, we kind of already know what temperature is going to be when it changes state. It's a liquid right now. We're going to try to, if we give it heat, what is it going to turn to? Yes. A gas, yes. Now, what temperature do we expect this to happen at? Remember, this is Celsius. What temperature should happen at? 100 degrees. you might not recall me saying this yesterday, but yesterday we were talking about the signs that you would see when it starts to change to a gas. How will you know it's changing to a gas? How will you know? Marissa? We'll see bubbles. What else might give it away? Eli?
The water will go down.
The level of water will decrease. And Aiden?
You'll see.
Yeah, we'll see the steam coming off of it. Now, as the gas spreads out in this container, we won't notice it as much. But I mentioned to you yesterday something about you will see bubbles before the whole thing hits 100. Do you remember that? Because it depends on where the heat's coming from. So eventually the whole thing will hit 100 and it all will start changing over. But parts of the water will hit 100 before the rest of the container hits 100. So you might see a couple of bubbles before it shows 100. And you understand why, right? Because the whole thing's not reached 100. Yes, now it's also going to show us in this viewfinder how the particles are behaving, the molecules of water, what they're doing. Okay, and you'll notice that when it hits the gas, what will these particles do when it hits gas stage? Spread out, go really fast. We'll see all that. So and even though water, we kind of know what's going to happen because we have those numbers memorized, 100 and 0. We kind of know what's going to happen. What I need for you to do, I need one person to watch the thermometer. So who'd like to watch the thermometer for us? Jacob, watch the thermometer for us. And I need another person to watch for bubbles. Jacob, you can't do both. So Addison, watch for bubbles. So Addison, when you see bubbles, you need to say now. When Addison says now, you tell what the temperature is. Okay, so you are only looking at the thermometer. Even though we kind of know what to expect, this is a good one to start with because for methanol and mercury, we don't know what to expect, do we? No. Okay, so let me hit play here. Let me scroll this up.
Are you talking about?
You're watching the temperature there. Sorry, I wasn't clear. So it's at 24 degrees Celsius. It's a liquid, okay? So here we go. So Addison, you say now and you see bubbles. And Jacob, you tell us what the temperature was at when. Notice how the particles are sliding past each other, increasing the temperature. Yeah, so it was at 100. And I saw a few bubbles before it got to 100. Did you? Yeah, and we talked about that. Okay, so now notice what the particles are doing. Faster, spreading out. We see the steam. We see the bubbles. Now, in your scientist notebook on your chart, write down what the temperature. So that was the boiling point. The water's boiling now. It's changing to a gas. What temperature was it? And put the capital C beside it, 100 degrees Celsius. We're going to cool it down now. So now we've got liquid water again. We're going to turn it to a solid. What's that process called? Freezing. So we're going to freeze it. Now, we're not going to have bubbles or steam coming off of it. However, they are going to still show us the particles. You can use the particles to tell when it goes into a solid. How will you know by looking at those particles that it's a solid? Will? Yes, they'll line up, they'll get a formation, and their motion, how will their motion be? Vibrating, shaking in place, okay? So I need one person to watch for the particles to line up. If you've already done it, put your hand down. I wouldn't choose you twice. Cole, you watch for it. So when the particles line up in formation, you say now. And then I need a thermometer person, Aiden. When Cole says now, you tell us what the temperature says. Now, since this is water, we kind of know what's going to happen. When do we expect it to happen? At 0, around 0. Okay, so here we go. Ready, Cole? So notice the particles are liquid. They're sliding past each other. Temperature's dropping. Yeah, so it's -1, so probably it was right at 0. Okay, so let's write that down. So the freezing point for water is 0 degrees Celsius. So we kind of already knew what to expect here. So now, on your chart that says freezing point, but remember we mentioned this morning that the freezing point is also called the what? Not boiling.
Vaporization.
No. The melting point. Nice, Kaden, the melting point. Because if the water is already solid and we give it heat, when it gets to 0 again, it's not going to freeze again. It's already frozen. It's going to start to do what? No, melt. It'll start to melt. So that 0 is the changeover spot. If it's a liquid, it'll freeze. If it's a solid, it will melt. So that's like the magic number there. Now, the next one we're going to do is mercury. We're going to heat it up first. And right away when we look at the viewfinder, you will see that the particles of mercury look different than the particles of water. They should, because, you know, water is made out of hydrogen and oxygen. Mercury is made out of mercury molecules. Well, no, they're going to change it. So I need a person to watch for bubbles. Laura, you watch for bubbles. Laura, when you see bubbles, you say now. And then I need a thermometer person. When Laura says now, you're going to tell us the temperature. Ian? We already know that water and mercury are very different from each other, right? Water boiled at 100 degrees. Do you think that mercury is going to boil at the same temperature that water does? No. Do you think it's going to need more heat to boil or less heat to boil? Mercury acts a little bit like water, doesn't it? Remember we saw the video of mercury, how it would pull together, and water does that, but does water pull together as strongly as mercury does? No, mercury really pulls together. The particles are really attracted to each other. I wonder if that's going to affect how much energy mercury will need to get it into the air. If they're pulling together really strongly to each other, it might need more heat. So we'll watch what happens at 100. Let's see if it's changed over by 100. My people, are you ready? Okay. Oh, we're already past 100. It's not a gas yet.
Whoa. Still not bubble. Now.
What was it? Okay, let's do it one more time. Yeah, I saw some too. So let's do it one more time. Here we go. Stay quiet so she can concentrate. When you look for the bottom there, you'll see bubbles.
Now.
306. Let's write that down. It sounds more accurate. In your scientist notebook, beside mercury for the boiling point, 306 degrees Celsius. Let's go to the converter. Okay, so it was, what was it? 306. 582 degrees Fahrenheit is what that's equal to. So did mercury need more heat or less heat to change to gas? Yes, a lot more. And we mentioned that the particles of mercury are strongly attracted to each other. They like to stick together. So if things are pulling strongly together, you're going to have to use more force to pull them apart. So it makes sense that it needed more heat to get it into a gas. Now we're going to cool the mercury down. Water turned to a solid at what temperature? 0. Now this one's a little trickier to guess. Do you think the mercury, you're going to have to remove more heat from it to get it turned back to a solid, or less heat? Eli, when they line up, you say now. Isaac, you tell us what temperature it is when he says now. Okay? Are we ready? We can do it more than once if we need to. So they're still sliding, so we know it's not a solid. There's 0, still sliding.
Now.
What was it?
-36.
Yes, -36, -36 degrees. On your chart for the freezing point of mercury, -36. So you actually had to get it colder than water does. You have to remove even more heat. And if you think about it, remember mercury, when we talked about mercury, we talked about how special it is, how that it's the only metal that's a liquid at room temperature. So you have to get it really, really cold to get it to turn to a solid. Let's see what that is in Fahrenheit since we're unfamiliar with those. -36. Oops. So 32 degrees below 0. Now our last one's alcohol. So for the methanol, we're going to heat it up first. Water turned to a gas at 100. Do you think the alcohol is going to need more heat than the water does to turn to a gas, or less? Raise your hand if you think more heat is going to be needed. Raise your, okay. Okay, raise your hand if you think less heat. Raise your hand if you're not sure. Fine, that's fine too. So let's see. we're especially paying attention to what happens around 100 degrees because that's when water changes over. Are you ready, guys? Look at those molecules, big ones.
No.
Oh, what? Whoa. What temperature's water when it turns to gas? 100. Alcohol only had to get to what? 58. Yes, let's write that down. 58 degrees Celsius, not much heat at all, and it turns to a gas. I want to bring up something that we talked about this morning when we were first talking about different kinds of alcohol, and I mentioned to you that at some restaurants, they have things on the menu like beer battered shrimp or bourbon steak, and, and kids might think, oh, if I order that, I'll be, putting alcohol in my body. Actually, no, you're not, because look at, let me pause this. Look at your chart. What temperature does alcohol turn to a gas? 58. So when you're cooking, when you get to 58 degrees, the alcohol is going to go where? In the air. So by the time you get done cooking, the alcohol is not in the food, just the flavor of the alcohol is there. The actual alcohol is now where? In the air. So order beer battered shrimp all you want. Let's see what 58 is in Fahrenheit. 136, yeah. And when we cook meat, the least temperature is 165. It's the least. And usually we cook things way higher, like in the ovens, 350, right? 300. So you can see that alcohol gets gone pretty quick when you mix it in, when you're using it to cook. And just the flavor is left behind. We're going to cool down the alcohol now. It didn't take much heat to turn it to a gas. Do you think we're going to have to remove a lot of heat to turn it to a solid? Water turned to a solid at 0. The mercury was negative 36, so 36 degrees below 0. Let's see what happens with the alcohol. Here we go. Oh, it's below 0 and still not lined up.
Oh.
Now it is. What was it?
I saw negative 97.
97. Let's do it one more time because he said now a little soon.
Yes.
Here we go. Yeah, so when they get in that formation, he saw them getting close to being frozen.
Yeah. I saw 98.
Negative 98? Yeah, so okay, we'll write that down. Well, he was in charge, so we'll take his word for it. If you'll put on your chart minus 98 degrees. We used to use mercury in thermometers. Now the liquid you see in thermometers, like this one here, is alcohol. Why is alcohol a good choice? Especially for an outdoor thermometer. Addison. Yeah, it has to get really, really, really cold before it turns to a solid. Let's see what that's equal to. It was negative 98 Celsius. Alcohol's not. No. Whoa. So I feel safe in saying it's not going to get that cold outside, right? And so alcohol is what we put in our thermometers because when it heats up, it expands evenly and it contracts evenly when it cools off. But also, we don't have to worry about our thermometer freezing up and being ruined, right?
But wouldn't it melt though?
It could, but remember, it's already melted. Alcohol, when it's a liquid, it's melted then.
I mean, couldn't it evaporate?
It could have been. Look how hot. Well, how hot did it have to get? How hot did the alcohol have to get? 58. So 100 and that was 136. Doesn't get 136 outside. Yeah. Yeah. Of the three materials, water, mercury, and methanol, the alcohol, which one needed the most heat to turn to a gas? Madeline. Yes, mercury. Now, of the three materials, water, mercury, and methanol, which one needed the least heat, the least energy to turn it to a gas? Marissa. Yeah, the alcohol turned to gas really quick, didn't it? Now, we mentioned a minute ago, stay with me, give me eyes, because I hope you're paying attention because this is going to help you in the experiment we're going to do probably Friday or Monday. You need to know this. We mentioned a few minutes ago that the reason we thought the mercury needed so much heat, what had to do with the particles being really attracted to each other. They like to stick together, so it needed more energy to pull them apart. The alcohol didn't need much heat at all to put it to gas, to turn it to a gas. So what do you think about alcohol's particles? Do you think they like to stick together as much as mercury's? Yeah, you need to sit up so your feet aren't kicking. Yeah, you're probably, if I had to guess, I would say the alcohol's particles aren't as attracted to each other as mercury's are, because it didn't take much energy at all to get them into the air. Look at the freezing point column. Which one needed to get the coldest? You had to remove the most heat from it in order to get it to go to a solid. Ethan? Huh? Yeah, the alcohol. You had to get it really cold. How cold did we have to get it? Negative, not 98. Negative 98. And which one needed the least heat removed from it in order to go to a solid? Aiden? Water, yes.
0 degrees.
Yes, 0 degrees.